Greetings, fellow nerds. As you know, I've been making sodium these past several months using the alcohol-catalyzed magnesium reduction approach. We had a lot of problems and we solved every single one, including trying to find a workable solvent, reaction times, processing methods dioxane, preventing glassware destruction, trying to dry reagents using easy-to-obtain drying agents like sodium and aluminum metal, and most recently we found two off-the-shelf catalysts for the reaction, including fortropiniol, which is easy to get but needs to be fractionally distilled from tea tree oil before use, and tetrahydrolinol oil, which can be used directly from the bottle but is somewhat hard to find and buy. In fact, very recently, as of this video, one of the very few online suppliers for it actually stopped selling it to new customers. So it's clear that tetrahydrolinol oil is not very amateur accessible. Fortunately, after an exhaustive search, I found another perfume and fragrance chemical that can be used: 2,6-dimethyl-2-heptanol, also known under the trade name of dimetol. I tested dimetol and it works just as well as tetrahydrolinol oil, finishing in 20 hours and providing a similar 95% yield. While it's not easy to find and buy the more viable off-the-shelf alcohols we have, the more likely it is the amateur chemist can find at least one. So I decided at this point to put everything together and make the final synthesis video. I washed my glassware and got out my old lab notes and started writing the scripts and experimental procedures. Eventually I started updating the reaction mechanism to reflect the things we've learned and observed so far. In the original mechanism I presented, water was a key intermediate for some of the steps. But now we know that even a tiny amount of water destroys glassware, and we were able to stop that by eliminating water. So the primary sodium production mechanism probably doesn't have much water in it. I thus wrote the mechanism this time using alcohol as the primary proton transfer reagent in addition to its original function as the metal transfer reagent. Now, the old mechanism might still be correct at high temperatures, especially when there is no sodium jumpstart. But eventually it transfers over to the new mechanism as water is completely depleted and there is available sodium to use in the new mechanism. Anyway, I wrote water up here for the sodium hydroxide drying step, but that's not part of the main reaction, so don't worry about it. It's just there for completeness. What happens is, first, sodium metal reacts with the alcohol present to make sodium alkoxide and hydrogen gas. The sodium alkoxide then reacts with water to make alcohol again and sodium hydroxide. Overall, this dries the water out of the reaction by destroying it with sodium and using alcohol as the catalyst. You might be wondering why I wrote out this way and not simply have sodium react with water directly. This direct reaction does happen, but it's slower. This is because most of the water is absorbed into the sodium hydroxide itself, so the sodium metal has to wait for the water to diffuse back out. The alcohol, being much less polar than water, diffuses much better in nonpolar solvents, so this alcohol-catalyzed drying reaction is much faster. This trick of using a mobile transfer reagent is used a lot in chemistry, especially when dealing with mixtures of solids or heterogeneous reagents. A transfer reagent that moves easily between two chemicals greatly speeds up the process. Anyway, as said before, I put this here for completeness. It's not actually important. Once all the water is depleted, it is no longer relevant or even part of the reaction. It's these next three steps that are important. I'm also going to write in step numbers for easy reference and to emphasize how important they are. We start with sodium metal reacting with free alcohol to make sodium alkoxide and hydrogen gas. Then we move on to reacting magnesium metal and sodium alkoxide to make sodium metal and magnesium alkoxide. This is the actual sodium production step. Finally, we have the magnesium release step where the magnesium alkoxide reacts with the sodium hydroxide to make magnesium oxide, alcohol, and sodium alkoxide. The cycle then repeats. Now, just because I can write down a mechanism doesn't make it true. I can similarly write down a mechanism involving tiny little elves moving things around, and that would also work. So I'm going to try and justify as many steps as I can. The easiest step to find evidence for is actually the second step. Magnesium reacting with sodium alkoxide to make sodium and magnesium alkoxide. We actually directly observed this way back in our theory testing experiment in May of this year. In that experiment, we first dissolved sodium metal in 7-hexyl 7-tridecanol to make the sodium alkoxide version of that alcohol. Then we dropped in magnesium metal, and just before we dropped in sodium hydroxide, we could observe what appeared to be tiny little spheres of sodium forming. They were very tiny, but they formed before we had added the sodium hydroxide. The sodium had to have come from a reaction with the sodium alkoxide already present. So this validates the second step. Now, validating the first step requires a bit more work. This reaction in itself is already well known and happens every day in labs around the world when they dry alcohols with sodium. In fact, we ourselves performed the exact same experiment in the theory testing experiment we were just talking about. We react sodium and 7-hexyl-7-tridecanol, and clearly it's producing hydrogen and making the alkoxide. So we're certain it can happen. But I say it's the harder step to justify because the real question is whether this step is the primary hydrogen generator in the actual alcohol catalyzed magnesium reduction reaction for producing sodium. I would argue yes. The best alternative mechanism is for magnesium to react and form the alkoxide. While this can happen, it happens at much higher temperatures. In fact, our whole Glasser destruction problem occurred because we needed higher temperatures to get the reaction going on magnesium alone without sodium jumpstarts. Temperatures that were also high enough to damage the glassware. But as soon as we used sodium jumpstarts, we not only avoided Glasser destruction, but the whole production reaction proceeded at much lower temperatures. So I think sodium reacting with alcohol is where most of the hydrogen formation is occurring. But I could be wrong. Maybe it's some sort of sodium-magnesium alloy that truly operates under these conditions, or even a weird zero-valent solvated magnesium atom. I don't know. But I have no reason at this point to consider alternatives since the theory testing experiment works on a similar set of steps. Now the last step is the hardest one to justify. Not because it can't work or is hard to perform, but just because I don't have an easy way of testing it directly in this system. Some sort of magnesium release reaction has to happen, but how it happens is up for debate. There is this reaction, as I read in here, but there can also be a two-step reaction where we have magnesium oxyhydroxide and alkoxide intermediate. This reaction is actually equivalent overall to the last one, but I don't have clear evidence for one or the other. There might even be surface effects. Like if this two-step reaction occurs, maybe the magnesium oxide release step only occurs on the surface of larger magnesium oxide particles. And this might be how the magnesium oxide particles grow in solution. This gets into the realm of solid-state chemistry and surface chemistry and possibly nanochemistry. As you can see, things can get really complicated really fast even in very simple systems. I'm going to invoke Occam's razor and just go with the single-step magnesium release mechanism, but I won't challenge anyone who comes up with evidence for an alternative mechanism that fits the data. Now, to help us see the catalytic cycle better, I'm going to write out our mechanism as a diagram. Yeah, it looks more complicated than NFL play breakdown analysis, but it's actually quite straightforward once you know what you're looking at. Here we have the first step in our reaction with sodium reacting with alcohol to produce sodium alkoxide and hydrogen gas. The sodium alkoxide reacts with magnesium to create sodium metal and magnesium alkoxide. Finally, the magnesium alkoxide reacts with sodium hydroxide to produce alcohol, magnesium oxide, and sodium alkoxide again. If you're wondering where water gets dried out, then it's not part of the main reaction, but we can draw that in a separate reaction if desired. I'm going to leave it out for now just to keep things simple. At this point, you're probably asking why I just wasted 5 minutes even describing this to you and why it's important. Once you have a nice and reasonably accurate mechanism built, you can start considering alternative chemistry and use your mechanism not as a description, but as a tool to create new reactions. Having a stepwise mechanism and a diagram helps us to better see issues and possible avenues for research. You know, I should frame this and hang it up on my wall. It's one of the very first amateur constructed reaction mechanisms here on YouTube. Anyway, let's move forward and see if we can use our mechanism as a tool to find better and faster catalysts. Examining the mechanism closely, it looks like steric bulk in the alcohol should affect the reaction. In chemistry, whenever you see two atoms or groups of atoms bumping against each other, but not directly bonded or reacting, we call that a steric interaction. If this affects the reaction somehow, like blocking reactivity, then we call that a steric effect. That's what I think is happening here. In case you're wondering, the first step isn't an issue for any alcohol since the change in steric bulk is very little. Sodium and hydrogen are both singly charged, and we're not really forcing together two bulky alcohols. Each alcohol bonds to its own sodium, so everyone is happy. It's the second and third step where things get interesting. Tertiary alcohols are very large and bulky and interact with each other near the magnesium. Think of it like two T-Rexes fighting over a steak. Although I'm not sure if steaks existed back in the Jurassic period. Anyway, they're so big that it's really hard for both of them to hold on to the steak at the same time. This is analogous to our tertiary alcohols, so steric bulk should play a role in how easy the reactions go. In the second step, steric bulk is increasing. Two separate alcohols must bond with one magnesium, so they're both bumping into each other. This step should be slower if we're using very big bulky alcohols. It won't stop though. This is a single displacement redox reaction, and redox reactions tend to have very high equilibrium constants, but the rate should be affected. The third step is what I call the magnesium release reaction. The sodium hydroxide enters the catalytic cycle and reacts with magnesium alkoxide to release the magnesium oxide and produce the various alcohols and alkoxide species. In this step, the steric bulk is decreasing. We're going from two alcohols bond to one atom to two alcohols bond to separate atoms. Now I know we're still unsure if this step is correct, or even if it proceeds in one step, but we do know that overall we have to go from magnesium alkoxide to magnesium oxide, and release two separate alcoholic species. So overall, the steric bulk around the magnesium has to go down. So steric bulk is actually favorable in this reaction as the relief of steric bulk drives it forward. This might actually explain why primary alcohols don't work. Since they have no steric bulk, they can't release the magnesium. But I would need to run some specialized experiments to prove or disprove that. Anyway, looking at the mechanism, we can see that if we use less and less bulky alcohols, we should improve the speed of the second step. And using bulkier and bulkier alcohols, we should improve the speed of the third step. So which one is more important? It looks like our direct experimentation has shown that using less bulky alcohols is more important. Going from 3-ethyl-3-pentanol to tetrahydrolenol oil improved the reaction times from around 30 to 40 hours down to 20 hours. Now I know we didn't need a mechanism to tell us that less bulky alcohols would be better, but having a mechanism lets us rationalize our observations. At this point, some of you might be screaming at the screen that tetrahydrolenol oil looks bigger than 3-ethyl-3-pentanol. So why am I calling it the less bulky alcohol? The answer is that the interesting chemistry is happening around the alcohol group. This is where the magnesium is bonding, and that's also where the steric interactions with other alcohols are highest. So the immediate environment around there is most important. This tail on the tetrahydrolenol oil is far away from the reaction, so it doesn't really react. The reduction of an ethyl group to a methyl group has a far greater steric effect in this situation than extending an ethyl to a long chain. So tetrahydrolenol oil is therefore called the less bulky alcohol, despite actually having more atoms than 3-ethyl-3-pentanol. Anyway, bottom line, tetrahydrolenol oil is less bulky and proceeds faster than 3-ethyl-3-pentanol. So can we do even better and faster? Unfortunately, it looks like we're at our limit. Going from tetrahydrolenol oil to dimethyl didn't improve things much. We could go even smaller to diamyl alcohol and T-butanol, but it's hard to accurately measure the rate as one of the problems I ran into was that they're volatile and boil out as the reaction runs. I need a condenser to keep them back in, but this introduced the further complication that now we have to worry about equilibrium vapor concentrations in the headspace of the flask. Another problem with T-butanol is that it actually freezes in the condenser since its melting point is higher than the cold water I'm using for the coolant. So accurately measuring them, let alone taking advantage of their performance, is difficult. In any case, neither alcohol is directly amateur accessible. We already knew they work, but they're not good candidates for amateur-friendly high-speed alcohols. Are we at a dead end? What if we go even less sterically bulky? What if we go with secondary alcohols? We might use ones that are bigger in terms of mass, but the steric bulk around the alcohol group can be smaller, even smaller than T-butanol. Unfortunately, as we've seen in our earlier experiments, secondary alcohols don't give very good yields. Interestingly enough, if we check our mechanism, there is something very big and very important missing. It doesn't explain exactly why secondary alcohols work badly. According to our mechanism, if an alcohol doesn't work, it should stop completely. It would get completely stuck on one of the steps because it binds magnesium too strongly or not strong enough. If it does work, then it should work completely. It might be slow, it might take days, but eventually it will run through and all alcohols should give us 80 to 90% yield at best. Tertiary alcohols behave consistently, giving high yields, even if they have radically different reaction times. Primary alcohols also behave consistently, completely failing to produce sodium. Secondary alcohols only partially work. Our mechanism doesn't account for that. We have relatively pure samples of secondary alcohols, so they should be working without interference. Unlike our experiments with raw tea tree oil or patchouli oil. Maybe for secondary alcohols there is some sort of side reaction. A side reaction is a reaction that happens with your reagents, but is not part of the main reaction under study. In that case, the side reaction destroys or alters your reagents and removes them from the main reaction. But the main reaction itself is still working fine. We already saw this with 4-terpineol being destroyed and requiring extra catalysts to be used. Maybe that's happening here. Now you're probably wondering why I'm bothering to pursue secondary alcohols. While our mechanism doesn't explain why secondary alcohols fail as catalysts, it does say that if we can get the catalyst to stay in the cycle, it should work completely. We just have to fix whatever the side reaction is. We would have a very different approach if the secondary alcohols didn't work at all originally. Then it wouldn't matter if we fixed whatever side reaction there was because the main reaction is broken. So I tried perusing the literature and finding every sort of reaction I could involving secondary alcohols or similar organic reactions that could explain what was happening. I looked at Oppenauer oxidations, but I couldn't figure out what the hydrogen acceptor was. I looked at E2 eliminations, but I couldn't reconcile why tertiary alcohols didn't suffer the same fate. I looked at alpha eliminations, but couldn't quite find a similar example to our conditions, and I went on and on for several weeks. Going on and on through dozens of reactions and hunting down all the literature I could, and then I realized something. I am a moron. And I actually mean it. I'm a moron in that I don't know everything. I'm trying to figure out what's going on, but I simply don't know enough organic chemistry to do so. Maybe the perfect mechanism that describes exactly what's happening is somewhere in the literature, but I don't know it. I'm not that smart. What I really should be doing is acknowledging I'm a moron and working within that constraint. I should be looking for categories of catalyst mechanisms and trying to figure out experiments to distinguish them. The actual number of mechanisms is unlimited, but the number of categories is quite limited. So while it would help to know what the side reaction is, it's more important that I stop it. So let's see what we can do. There are deprotonation decay pathways. Once you remove a hydrogen using a strong base, the resulting carbanion is very reactive. Maybe we're doing that to the alpha hydrogen. Unfortunately, there is no simple way to stop this other than using a tertiary alcohol, which defeats the purpose. So we move on and hope that isn't it. A catalyst loss mechanism that's not often talked about but still well known is physical loss into the product. We're making a heterogeneous side product, magnesium oxide. It's not hard to conceive of the catalyst getting stuck inside. Looking back at the mechanism in the magnesium release step, what if the release is only partial? Over time, we're making a non-stoichiometric magnesium oxyalkoxide. But if we don't get the catalyst back out, it's lost. What's interesting about this loss mechanism is that the alcohol isn't actually being destroyed. It's just lost. So all we have to do is stop the loss. Fortunately, we can do that by simply making it not fit onto the magnesium oxide lattice. Tertiary alcohols do this by being too bulky right at the alcohol group by the alpha carbon. We might be able to achieve the same effect further away by adding steric bulk on the beta carbon. Our failure with norlimbinol shows that we can't be too far away with steric bulk, so we need to be closer. So let's put that in the idea pile for now. Moving on, what if there is a free radical decay mechanism? Maybe we're making free radicals at the alpha carbon, and that's leading to unwanted side reactions. Most ways of suppressing free radicals is to add a radical scavenger. Something that itself reacts with free radicals is preferable to the target reaction. But I'm worried that those substances would introduce unwanted reactivity. So for now, I'm not going to try and stop it. But if nothing else works, we can come back to this and start adding in radical scavengers. Okay, next catalyst side reaction candidate is some sort of rotationally relevant reaction. There are some reactions in organic chemistry that only work if you can rotate the two carbon atoms involved and their substituents so that they align. If you allow free rotation, then the reactions happen. If you block rotation, you can stop the reaction. If you pre-align these substituents, you can encourage the exact reaction you want and block others. One of the most well-known of these classes of reactions is the E2 elimination reaction. Now I'm skeptical about E2 eliminations happening under our particular reaction conditions, especially since our tertiary alcohols should also have decayed. But if there is some sort of rotationally relevant reaction, then the solution to block it is to use a rigid alcohol that restricts rotation. So let's put that in the idea pile for now. Our next candidate is some sort of metal and single molecule reaction. For example, a hydride transfer reaction. There's unfortunately very little that can be done about this other than using tertiary alcohols or different metals. Both of these options defeat the purpose. So we'll just have to cross our fingers and hope for the best. The next candidate is instead a metal and multimolecular reaction. An example of this is the Oppenauer oxidation, where you need two organic molecules coordinated to the same metal atom to react. While I don't think the Oppenauer oxidation is happening here exactly, maybe the two alcohols bound to magnesium are doing something. Blocking such a reaction is very hard, but we can slow it down by again increasing steric bulk and rigidity and make it difficult for the alcohols to align properly and do whatever weird and freaky things they're doing. Basically, we want to block any chemistry between them by making them really fat and unattractive to do so. Now at this point, since we're repeating criteria, I think we can start looking for alcohols that best fit them. This doesn't mean that there isn't more reactivity to look for. For example, there might be acidity issues that can be adjusted with different substituents. But now that we have enough ideas, we should start proving or disproving them to narrow down our search. Maybe we got lucky and have already stumbled on the critical catalyst removal mechanism. Anyway, what sort of secondary alcohols fit our criteria? The first and easiest to get candidate is menthol. It looks just like our original 4-terpineol, but fully hydrogenated with the alcohol group moved over one carbon. In this position, it's a secondary alcohol. This is why it was originally rejected earlier on. But now that we have a possible reason why it should work, it's back on the table. The isopropyl group here makes it very sterically bulky around the alcohol. So hopefully this will reduce any physical loss mechanisms by making it very hard for the menthol to get stuck in the magnesium oxide lattice. The ring structure severely restricts rotation. While the molecule can still bend and flex into different conformations, hopefully we've blocked enough that we can shut down whatever decomposition mechanisms is dependent on them. Alternatively, if we get total destruction, we'll know that we somehow favored that reaction and we'll be able to engineer an alternative. So I ran the test with menthol. 20 grams of sodium hydroxide, 15 grams of magnesium metal, 150 milliliters of mineral oil, 3 grams of sodium metal jumpstart, and 2 grams of menthol. And after 30 hours it worked. I ran the usual processing with dioxane and got 13.5 grams of sodium metal. As usual, our 3 grams of sodium metal jumpstart means we really got 10.5 grams of sodium and our yield was 91%. This is a major improvement for this process. Menthol is extremely ubiquitous. While not as ubiquitous as tea tree oil, it is nonetheless sold by so many suppliers around the world that finding it is pretty much a non-issue for the amateur. It is directly usable and doesn't require any sort of processing like tea tree oil. So while tetrahydrolenol oil and dimethyl might be better performing, menthol is the more reliably sourced catalyst. I think menthol is going to be the main catalyst I feature in my videos. On the theoretical side, we've also been able to validate our reaction models. Granted, we still don't know exactly what the issue is causing secondary alcohols to work badly, but we nonetheless have a working solution to prevent it. And this wasn't some accidental discovery. We made a theoretical prediction and tested it. All of this work is starting to assemble into an actual publishable scientific theory. Now, something interesting about menthol. It took about 30 hours to run. It looks like we went too far and used too much steric bulk. We can probably improve our reaction rate by dialing the steric bulk back a little. But we have to be careful about running into one of our catalyst removal side reactions. If it turns out the hypothesis of steric bulk preventing catalyst loss into the magnesium oxide lattice is true, then reduction of steric bulk would be a problem. Fortunately, we got incredibly lucky, and there is another off-the-shelf catalyst that has the features we want. Endo 177-trimethyl-bicyclo-2,2,1-heptane-2-ol, better known as borneol. Let me explain the structure a bit. It has a more complex 3D structure than menthol. It has a 6-membered ring just like menthol, and bridging over on top are these 3 carbons. What's important to focus on is this alcohol and the fact that the substituent next to it is this methyl group. This is much less bulky than the isopropyl group that was beside the alcohol in menthol. So this should react faster, as magnesium atoms and sodium atoms can easily access the alcohol group. The short-range steric bulk is reduced. Interestingly enough, this bridging structure makes this whole face with the alcohol rigid and bulky enough that it can't get lost into the magnesium oxide lattice. The long-range steric bulk is increased. Borneol manages to improve long-range steric bulk while decreasing short-range steric bulk. It's also extremely rigid like menthol, so if rotationally relevant reactions are the issue, then they should still be blocked. Okay, this all sounds good on paper, but let's test it. So I ran the reaction using borneol now. 20 grams of sodium hydroxide, 15 grams of magnesium, 150 milliliters of mineral oil, 3 grams of sodium jumpstart, and 1.4 grams of borneol. And it worked, slowing to a crawl in just 10 hours. It's the fastest catalyst we've ever had. I processed the reaction dioxane to get a yield of 13.1 grams. Our actual yield is 10.1 grams or 87%. This is impressive. Menthol took 30 hours to work, but with careful catalyst selection and looking for exactly the features we wanted, we were able to get that down to 10 hours with borneol. Unfortunately, borneol is like tetrahydrolenol oil. It's not as common as we'd like for a reliable and amateur-accessible reaction. Nonetheless, for you highly resourceful amateurs, borneol would probably be the catalyst of choice unless we find a better one. I planned in earlier videos to hydrogenate tea tree oil or lavender oil to make our catalysts. But now that we have menthol and borneol, I think it's no longer a pressing issue. If we really want to make a high-speed catalyst, then our efforts are better spent making borneol by the reduction of camphor. This is actually an easier reaction for the amateur since it doesn't use annoying-to-handle hydrogen gas. Overall, it looks like we have our final catalyst, menthol. It's directly usable without the need for any purification or processing, and doesn't suffer the decomposition problems like fortepiniol from tea tree oil. While it doesn't seem to perform as fast as tetrahydrolenol oil or borneol, taking about 30 to 40 hours to work as opposed to tetrahydrolenol oil's 20 hours or borneol's 10, I still think the wide availability makes it the better choice. You know, when I started this project, I thought the best catalyst would remain tertiary alcohols. But it appears we might have 2 secondary alcohols as our top catalysts. Menthol is especially amazing in how conveniently accessible it is. Anyway, this video has been a tremendous 2 steps forward. To summarize what I'm sure was a very information-dense and extremely technical and confusing topic, we've gathered all our observations so far and rewrote our mechanisms to incorporate our new understanding. We verified a few steps to be certain we weren't completely wrong. We realized that there was a major gap in our understanding regarding secondary alcohols. We used what we did understand to categorize what we didn't know and make broad but testable hypotheses about what sort of criteria we needed to make secondary alcohols work. We finally tested a couple of off-the-shelf secondary alcohols that met our criteria and found they successfully gave high yields of sodium. In doing so, they validated our selection criteria. Not only that, but we also made a tremendous improvement in reaction speed, cutting our best time of 20 hours down to 10. I think this shows the importance of research, understanding what we're doing, and building theories around it. Earlier on, we were just testing things empirically and spent months making slow and steady progress, trying everything we could find. But now that we have a reasonably working model, we were able to peer into the inner workings of the process and even engineer our reactions to some extent. Over the course of just one video, we solved why secondary alcohols didn't work, why it was worthwhile to get them to work, finally suppressed what was making them fail, and proved they did indeed work. Then we went even further and made them even better than our best tertiary alcohols. This sort of research before would have taken months of trial and error. That's what real scientific insight gives you. In fact, I'll be honest, making and editing the video itself took longer than doing the experiments. I think it's also important to mention that we still don't know exactly why secondary alcohols fail, being unable to use a problem-based approach as we didn't know what the problem was. We instead approached it from a solution-based perspective and tested solutions that could fix multiple problems. In real research, you don't often know a great deal what's going on, but you can still apply overarching rules and conditions to leverage what you do know and still perform useful experiments that encompass them. Anyway, at this point you might be asking, where do we go from here? On the theoretical side, we still don't know exactly what the secondary alcohol catalyst removal mechanism is. We know it might have something to do with steric bulk or structural rigidity. The most informative experiment would be for me to test cyclohexanol as a catalyst. It has structural rigidity, but no additional steric bulk compared to something like norliminol. If it works badly or fails, then the removal mechanism has something to do with steric bulk. But if it succeeds with high yield, then we know the mechanism is a structural issue. Unfortunately, I can't get cyclohexanol, so this experiment may remain unfinished. But that's not a problem for us. This information is only important on a theoretical level and only necessary if I want to publish my findings in a peer-reviewed journal. Us amateurs, however, are more concerned with practical improvements. So on the practical side, I'm not sure where to go next actually. I can keep looking for catalysts, but I'll be honest, I'm not sure if I can find something even more accessible than menthol. But knowing that secondary alcohols are back on the table opens up a huge array of possible candidates. Who knows, maybe a primary alcohol can work. I said before the cetyl alcohol experiments nailed the coffin shut on primary alcohols. Now, I think I might be wrong. Maybe there exists out there a special primary alcohol with particular structural features to work this reaction. I don't know, but that's what makes research exciting. Another thing I could look into is alternative solvents. Now, nothing will beat mineral oil in how easy it is to get, but there might be solvents that work much faster or have other useful properties. Anyway, I keep saying the final video will be out soon, and I keep pushing it back due to these annoying rashes of new discoveries. I just want to say I'm sorry for the delays. I thank you all for your patience. I will get to it, hopefully I don't make some other discovery in the meantime. Thanks for watching. Anyway, this video was a lot of work, probably my longest video yet that isn't a compilation of topics. I really appreciate all my patrons on Patreon for supporting me and donating to the cause. I probably never would have gotten this far and made this sort of breakthrough without you. Hopefully I can keep them coming. And if you aren't a patron right now, I hope this video shows a little more of what we can do together. So please consider donating.